Last class I told you a shear strength. Shear strength is equal to C plus sigma tan phi. No? Then I told you that here this is C and tan phi is a constant, and this sigma and tau is variables. As you increase this one, then tau will increase, right? And I already gave you some example like sigma is 10, then tau will be 5, then sigma increase to 20, then tau will be something 8, or 30, then tau will be something 25, whatever it is. No, some random numbers I am giving you. Means here what it understands is shear strength of the soil is not a constant. Shear strength of the soil is not constant unless that this one compared to that steel or concrete, there the strength is very constant, but here it is not constant. Okay, like this how much we can apply, there should be some limit. At a particular limit the soil will fail, soil will fail. That failure or otherwise how much the soil is ready to take that load is considered as a bearing capacity. Bearing capacity means soil how much is ready to bear the load, that is called as a bearing capacity, that we are studying today. The chapter name is bearing capacity. Before that we should understand, because slowly we entered into foundation engineering. This is the introduction to the foundation engineering, this chapter, but therefore we have to understand what is foundation, and later we'll enter into the bearing capacity. Now look at here, foundation means what? Foundation is a part of the building. Let us consider this is a building, then this building is kept on the ground. But this is not stable building if you keep it just on the ground. Therefore, you should insert some part of the that building into the ground so that it will be stable. The top portion will be stable. This top portion is considered as a superstructure, and bottom portion is considered as a substructure. Okay, then what is the foundation? Foundation is a substructure. Okay, this is a part of the building. This is a part of the entire building, which is also called as a substructure, and the function of this one is it is transferring the load from superstructure to the ground. Here what is there? Here a soil is there. This is a soil, and from here the load is transferred. The load is transferred to foundation, and foundation in turn will transfer the load to the uh, load to the ground, so soil. This is called as a foundation. Then in that foundation we have a two categories. The first one is a shallow foundation. The first one is a shallow foundation, and the second one is a deep foundation. What is the meaning of shallow foundation? Shallow means near to the ground, that is a shallow. Shallow means small, swalpa. Now let us consider, you have a footing like this. You have a footing like this. This footing is of 2 meter breadth. Then how to define a shallow foundation is, if you get a hard starter, let us consider this is your hard starter. This is your hard starter. This hard starter you are getting less than 2 meter. You are getting less than or equal to 2 meter. Means it might be 1 meter or 1 meter, 1.5 meter, like that. Then if you are getting a depth less than the breadth, then this foundation I will call it as a shallow foundation. Means what is the definition for shallow foundation? Where depth is less than or equal to breadth. That is your shallow foundation. Then what about deep foundation? Deep foundation is if this footing only you are keeping it in the soil, but your depth of the hard starter is very far. This is hard starter. This hard starter depth is very far. How much far? Let us consider this is a breadth b, and this depth is very far compared to the breadth. Then I will call it as a deep foundation. Now you got two different type of foundation, that is a deep foundation and shallow foundation, right? Now in a deep foundation we will be having few classification. Sorry, in shallow foundation, in shallow we will be having different uh, again the classes. They are called as a footing. Okay, what is a footing? Footing means just one column load or two column load, which we will consider it as a footing, right? Usually the shallow foundation, another name for that one is a footing we can call. Now in the footing we will be having one column footing. One column footing can be like this, or one column footing you can have some inclined portion, and after that you can have a spread. Then after that you can have like a stepped footing also. Okay, and see here, this is isolated. Now this column is isolated. Isolated means separate. It is individually acting, it is separate from the means compared to entire foundation. Therefore these three footings we can call it as a isolated footing. Isolated footing. Isolated footing, in that one, this I will call it as a spread. It, the load is spread here, spread footing, and this is a inclined footing, inclined spread, inclined spread, and this is a stepped spread, stepped footing. Correct? Like this. This is single column. If we have a two columns, one column here and another column here, then these two columns are very near to each other. Therefore, we will provide this type of footing is called as a combined footing. Combined footing. The cross sectional area of the combined footing, if you see, it might be a square cross section, sorry, rectangle cross section. Usually rectangle will be given when this load and this load is same. When two loads are same, then I can give the rectangular combined footing, rectangular combined footing, and I can give some trapezoidal combined footing also when this column load is something q and this column load is something p, where q is greater than p. In this case also I will give a trapezoidal combined footing. No? The cross section of these isolated footing also you can consider. The cross sectional area, the bottom area can be circular or can be square or can be rectangle. No? These three variations you can get: circular footing, square footing, and rectangular footing. Right? Now you got the types of footing. Now we have studied single column footing and two column footing. Then if you have several column footings like one column here, another column here, another column like that, and you are giving one common mat for this one. When you are giving many number of columns and common platform for that one, this platform is called as a mat, or sometimes it is called as a raft. Therefore this is called as a mat footing or mat foundation or raft footing or simply raft or raft foundation. Okay, these are your types of footing. Then like that, the D foundation, if you go in a D foundation also we have a classes. The first one is a pile foundation and well foundation. Then after that we have a Kaizen. Kaizen is also something like a well foundation only, but this is very big in diameter and they are little bit small in diameter and they are very small in diameter. Alright? There might be here also pile foundation also. There are many that you can go through the theory. You will be getting that concrete piles, timber piles, composite piles, homogeneous piles. Like that cross section also. Circular pile, square pile, rectangular pile, then H pile, hollow piles, like that, and installation also drilled pile, hmm, cast in situ piles, like that, and hammered piles, like that. You will be having many other types of pile foundations, right? Now we will go to bearing capacity chapter. Now the concept is here, if this is a footing, and the footing is in shallow depth, because this is your hard strata, and this is your soil here. This is also soil and this is also soil. Below the soil is a very hard, therefore, and this is your particular soil at a depth D, right? Now you will be applying some load Q here, and this below soil should not fail, should not fail. First criteria. The second criteria is should not fail in shear, should not fail in shear, the first criteria. Second criteria is settlement should be, settlement shall be within permissible limit, within permissible, within permissible limit. These two criterias, whenever I want to safety of the foundation. If you want to say the footing is safe, then you have to ensure these two criteria. The first criteria is soil should not fail in shear, and the second criteria is settlement should be or shall be within the permissible limit. Right? Now, how to satisfy the second one? I will just give in 1 minute. That is how to satisfy the second one. The settlement should be within the permissible limit. How to satisfy this one? We already studied the total settlement equal to immediate settlement plus secondary, primary settlement or consolidation settlement and secondary settlement. All together you will add up and you will get something 20 mm or 30 mm, whatever you will get it. No? Then after that, IS code will give you some standard permissible settlements. Let us consider a permissible settlement for a particular foundation, isolated footing on particular soil. If it is a 25 mm, then look at here. Your footing, the sum is 20 mm, and the standard given by the IS code is 25 mm. Therefore, you can say the foundation is within the limit. Understood? The first second criteria is very easy to satisfy. Means in calculation, theoretically, that is very easy to understand. The first criteria is soil should not fail in shear, that we will be going through. Right? Then according to how a soil will fail below the footing, that will be there. Okay. Now concentrate here. I will be asking you questions and you have to answer. Okay. Now look at here. This is a soil. This is a soil. Sorry, this is a footing, and on this footing I am applying load Q. Okay, and I have another footing also here. I have another footing also here. Here also the load Q is applied. Okay, this you can call it as a Q1 and Q2, whatever it is. Now the hard strata I am getting here. The hard strata I am getting here. Here also I am getting the hard strata. The depth is D here and depth is D here. Breadth is B here and breadth is B here. Means I have two different conditions. I have two different conditions. The first condition is I will consider the soil below the footing. Soil below the footing, concentrate. Soil below the footing, not this soil. Okay. Soil below the footing fails in general shear failure. General shear failure. Soil below the footing will fail in general shear failure. Then in the second case, I will consider the soil below the footing will fail in punching shear failure. Punching shear failure. See here, I am considering punching shear failure. Actually, this is the first one and this is the third one. There is another type of failure. That failure I will write it here. This is a footing. This is a footing. This is a hard strata, and this will be a local shear failure. Local shear failure. I will be asking you questions, you have to answer. Before that, I am explaining the theory. Later, I will ask you questions based on your intelligence, you can answer that. Now, this is your footing. What is the meaning of general shear failure? The meaning of general shear failure is when you apply this load, then that load will be applied to the hard strata, that is transferred to the hard strata. Because of that, this hard strata will bulge considerably. It will bulge very largely, and this effect you can see at the top also. On the ground also you can see the bulging effect. Okay, this is called as general shear failure. Understood? Now, the third one is punching shear failure. Here, when you apply some load Q here, because of that, this foundation will go inside. The foundation will go itself, the foundation itself will go inside, and you will not observe any bulging in the hard strata level. Therefore, you will not observe any bulging in the ground level also. No bulging. But when you compare here the local shear failure, when you apply the load, then little bulging will be there here. very little bulging, and that little bulging you can observe, very small bulging you will observe in the top portion also, the ground level also, right? Now this is a explanation about a general shear failure and local shear failure and punching shear failure. Now my first question is which type of soil will experience, no, whether this I will consider case 1 and this I will consider case 2. Now you have to answer me, the case 1 soil is dense or case 2 soil is dense? Which is more dense?
Case 1.
Others? Case 1 soil is more dense or case 2 soil is more dense? Because in case 1 general shear failure is happening and bulging is there, and case 2 there is no bulging, punching shear failure is happening. Okay, the one answered this one, case 1, can you explain me the reason?
There will be denser packing of the particle,
Hmm.
so the stress distribution will be better in this case.
Hmm. But why that bulging is there? You already given the answer. Correct answer is the packing is very
The
denser.
packing will be more. There are no voids for the rearrangement of the soil particle,
Very good.
so it
Correct
is
answer.
coming out of the box.
Correct answer. Okay, 100% right answer. Because here the particles, I already said that this is a dense soil. Sorry, already said there is a bulging here, means this will happen in dense soil only, because if the soil is very dense then there is no void, then this will penetrate inside with some and how much it will penetrate, no, that much it has to bulge here, and the same amount will be bulging in the top, and you can see this one, means from this you can understand that whenever you push the foundation down, then if you are observing bulging in the ground surface, then the soil below the footing is dense soil, then it is good or bad? Bulging, if you are seeing in the foundation, then that is a good or bad? Then the answer is good. General shear failure indicates that is a better soil, good soil. Now coming to here, this soil is a loose soil, will you agree or not? Or here also it is a dense? Okay, this is a loose soil. Why it is loose soil? Because it is entering inside without any bulge, means there are more voids in this position. Oh, no, the soil has a more voids, therefore it is entering inside, therefore we are getting that settlement, more settlement, but there is no bulging, therefore I can say it is a loose soil. The second question is, I want to say case 1 and case 2, sand and clay, which will be case 1 and which will be case 2, sand and clay, out of these two? My question is,
Ca-
yeah, tell me.
Case
Clay is
3,
there.
case 2 will be sand, case 1 will be clay.
Okay, others? My question is just simple, the sand is more dense compared to clay or clay is more dense compared to sand?
Clay is more dense.
Clay is more dense than the sand. Okay, others, any idea, arguments? Okay, now I will ask you one general question. Look at here, ಗಿರಣಿಗೆ ಹೋಗಿದ್ರಿ ಎಲ್ಲರೂ? ಗಿರಣಿ ಅಂದ್ರೆ ಗೊತ್ತಲ್ಲ, ಹಿಟ್ಟಿನ ಗಿರಣಿಗೆ ಹೋಗ್ತೀರಿ, ರೈಟಾ? ಚಕ್ಕಿ, ರೈಟಾ? ಹಿಟ್ಟಿನ ಗಿರಣಿ ಹಿಂಗ್ ಬರ್ತಿರ್ತೈತಿ, ಹಿಟ್ಟು ಬರ್ತಿರ್ತೈತಿ, ರೈಟಾ? You will put here a grains. You put a grains. Let us consider you went to this chakki or girani. There you took one bag of rice. Let us consider this is the 2 kg rice grains you have taken. The particles are this much. Then after that, there is a powder here. Rice flour will be there. This will be equal. You will bring in a same container or a different container. ಬರ್ತಾರೆ ಚಂದ ಆಗಲಿಲ್ಲ ಕ್ವಶನ್ ಸರಿ ಆಗಲಿಲ್ಲ. I will ask you one bag of rice, one tight bag of rice. You took it for chakki, and after that, will you come with the one bag of rice, or two bag of rice flour, or half bag of rice flour?
More than the taken volume.
Right? Very good. Means okay. Now the second question is 2 kg rice you have taken here. Means when you bring it is a 2 kg or less than that or more than that.
It will be equivalent.
Okay. Now see here, the rice grains are bigger and the flour grains are smaller. Flour grains are smaller. Now rice is 2 kg divided by volume is the density, and here the floor is 2 kg divided by volume, but this time volume is more here, therefore density is less. Therefore here the volume is less here, therefore density is more. Now density of the rice grain is more or density of the floor is more? Density of the
Rice.
rice grain will be more, density will be more here. Density of the, now tell me, density of the sand is more or density of the clay is more for a particular volume? Hmm? A truck carrying sand is heavier, a truck carrying black cotton soil is heavier. Which is heavier? Huh? Therefore the density of the sand is more, the density of the clay is less. Understood? The second thing, sand will be having more voids or clay will be having more voids?
Sand, sir.
Ah, same example once again go through. ಹಿಟ್ ಮಾಡಿಸ್ಕೊಂಡು ಬಂದ್ಮೇಲೆ ಅದು ವಾಲ್ಯೂಮ್ ಜಾಸ್ತಿ ಆಯ್ತಲ್ಲ, ವಾಲ್ಯೂಮ್ ಜಾಸ್ತಿ ಆಯ್ತಂದ್ರೆ ಎದಕ್ ಜಾಸ್ತಿ ಆಯ್ತದು? ಅಕ್ಕಿ ಹಿಟ್ ಮಾಡಿಸ್ಕೊಂಡು ಬಂದ್ಮೇಲೆ 2 ಚೀಲ ಆಯ್ತಲ್ಲ, 2 ಚೀಲ ಆಯ್ತು ಅಂತಂದ್ರೆ ವಾಲ್ಯೂಮ್ ಜಾಸ್ತಿ ಆಯ್ತು. ವಾಲ್ಯೂಮ್ ಜಾಸ್ತಿ ಆಯ್ತಂದ್ರೆ ವೈಡ್ಸ್ ಜಾಸ್ತಿ ಆಯ್ತಲ್ಲ ಹಿಟ್ಟೊಳಗ. ದೆನ್ ಸ್ಯಾಂಡ್ ಒಳಗೆ ವೈಟ್ಸ್ ಜಾಸ್ತಿ ಆಯ್ತು, ಹಿಟ್ಟೊಳಗ ಕ್ಲೇ ಒಳಗೆ ಹಿಟ್ ವೈಟ್ಸ್ ಜಾಸ್ತಿ ಆಯ್ತು. ಹ್ಮ್, ಗೆಟಿಂಗ್ ದ ಪಾಯಿಂಟ್? ನಿನ್ನೆ ಲಾಸ್ಟ್ ಹೇಳಿ ನೋಡ್ರಿ, ಡೋಂಟ್ ಯೂಸ್ ಯುವರ್ ಕಾಮನ್ ಸೆನ್ಸ್ ಅಂತೇಳಿ. ಹೌದಲ್ಲ, ಬಹಳ ಇಂಪಾರ್ಟೆಂಟ್. ರೈಟಾ? Now look at here, why our common sense is always giving hand? Huh? Now look at here. The first, when you think the sand will be more, means now you come to know that the density of the sand is more, density of the sand is more, and wides also, wides are less in sand, then wides are more in clay. Still our common sense is not agreeing this one, correct? Your common sense is not agreeing. Now tell me, wides in gravel is more or more than sand or less than sand? Wides in gravel is more than sand or less than sand?
Depends
More
on
than sand.
grading.
You will take a uniform grading sand, uniform grading gravel. whites in gravel, whites in sand, whites in clay. Arrange them in increasing order.
Gravel, sand. Mm.
Increasing order means lesser you are telling. Gravel means less whites.
Yes, yes, sir. Yes, sir.
Okay, sand will have more whites. Then clay will have more whites. Correct? Huh?
No, sir.
Correct answer. Gravel will have a less whites. Sand will have more than the gravel. Then after that, clay will have more than the sand whites. Now still your common sense is not agreeing. Why? Because your common sense is going through the sizes of the whites. Sizes of whites. Look at here. I have one big gravel here and another gravel here and another gravel here. Okay, now three gravels are there. Now, how much wide is there here? This much wide is there here. Correct? This much wide is there. If I make this one in a triangle container, then I have a here wide, here wide, here wide, here wide, here wide, and here wide. You may think that sir, wides are more, no here. Okay, wides are more here. Okay, I will take a same triangle here. I will take a same triangle here. Now I will make the pieces of these small that gravels into small pieces. Then I will put it here. No? Small pieces I made and now I have put them here. Now count the whites. Count the whites. Here whites, 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 whites. See here, as the particle size is getting no, then if you sum all of these whites, then what? The whites are more here, then whites are less here. But size is more here and size is less here. Correct? When I go to the clay soil, when I go to the clay soil, then soil will be particles are very smaller particles. I cannot make it entire thing. Just I will show it here only, this much only. Okay, no? Then what about whites? How much whites are there here? Everywhere whites are there. Everywhere whites are there here. Correct? Therefore, more whites are there. Understood? Now, permeability is more in which of the soil? Tell me, gravel, sand, and clay. Permeability is more in, huh?
Gravel.
Huh?
Gravel, sir.
Okay, permeability is
Gravel.
more in gravels. Okay, now you should not tell like this, sir. Permeability will be, why permeability is there? Your common sense will tell like this. Now look at here. Why there is a permeability? Because soil has a wides. Okay. Then clay has a more wides. Yes, sir. Then clay must have a more permeability. No. Gravel has a more permeability, but gravel has a less wides. Then permeability is depending on wides or what?
Interconnected words.
Very good answer. Now the permeability is depending on interconnected voids and interconnectivity is more in gravels and sand. Therefore, the permeability will be more here. But clay has a more voids, but there is no interconnection between those voids. And even there is a charging also here in the clay. Therefore, permeability will be very less here. Now coming to our chapter, this concept you should not forget. Coming to our chapter, this one. Here you can see this is a dense one, therefore bulging you are saying this is a loose one, therefore there is no bulging. Correct? Now, which type of soil? This will be observed in a gravel type of soil and sandy soils. Okay, na? Hard strata, sandy type of soils. Then you will get a general shear failure. When you come here, it might be a clay type of soil. Clay type of soil. Now tell me, if I want to, then this is a clay soil means what? I can say that C is present here, phi equal to 0 soil, no? Then here I can say the phi is very more large. phi is very large. Therefore, the general shear failure is predicted when phi value is more than 36 degree. Okay, more than 36 degree. In some textbooks or some authors, they will allow it for 28 degree also, more than 28 degree also, but we'll remember more than 36 degree means the soil is very gravel or sand. In that nature, you will get this bulging or otherwise general shear failure. Then White's ratio, what do you say? White's ratio is less less than 0.5 or something. That list I will chart I will send you. This is White's ratio. Right? Like that we have to think. Then the punching shear failure. Here it is there. I will give you now only 1 minute. Sorry, White's ratio. I don't have. I will give you White's ratio later. This phi value is greater than 36 will remember, and E value is less than 0.5 will remember. And just you remember here, I will tell you later, that is N value, SPT N value is more than 30 here, and this is N equal to almost 0. Then we have another one, no, another punch, the local shear is there. The local shear is here, the phi value is less than 28 degree, less than 28 degree, and SPTN value is less than or equal to 5, less than or equal to 5. Then here relative density ID is less than 20, and here the ID is, here the ID is greater than 70. ID is relative density. Understood? These are the notations. And I am not giving any values for this punching shear failure, because whenever you get a punching shear failure in soil, then you should avoid that soil or otherwise stabilize that soil, improve the bearing capacity, then you build. Therefore, most of the time punching shear failure bearing capacity is not determined. Right? And when I apply some load and study the graph here, then load versus settlement graph, look at here, this is your load, and this one is a settlement, this is settlement. Then you will see this nature for general shear failure, and you will see this type of nature in local shear failure, and you will observe the down decrement. This is your punching shear failure. Okay, general shear failure, you will get a bearing capacity for a particular settlement just drawing at a peak point. You will consider the peak point, then this is your load. And local shear failure, you will draw one tangent here and you will draw another tangent here. The tangent where they intersect, that point you will consider it as a load. And here punching shear failure, you will draw one parallel line or otherwise this projection, then you will get a load here. Punching shear failure is always ignored. General shear failure and local shear failure, for that we will be studying the bearing capacity. Now further going to general shear failure, if this is the foundation, this is a footing, then this is your hard strata, then this is your ground level, you will apply the load, then the below the footing there is a soil. Below the footing, this soil will fail in 5 zones. Below the footing, the soil will fail in 5 zones. The first zone is this one, and this is a second zone, and this is a second zone, means 3 zones are there. Now this is a third zone, and this is a third zone. Few textbooks they say that 3 zones are there, and few textbooks they say that 5 zones are there, but ultimately this is the diagram. Now this is called as a wedge. This is considered as a part of the footing, part of the footing. It is also called as a rigid wedge, rigid wedge. Okay, and this surface from this to here, you will be having a radial shear failure. This is a radial shear failure, and this is also radial shear failure, and this one is a linear shear failure. This is your linear shear failure. Okay, now this is all about general shear failure. And when you come for a local shear failure, then this is your foundation, ground level, hard strata. Then here you will see wedge, the rigid one, part of the foundation. Then you will see small portion of radial failure only. Then you will not find any linear failures. Okay, this is your local shear failure. Then punching shear failure, no zones. Okay, then punching shear failure, it will just directly it will enter inside, therefore you will not make any zones here, right? These are all three types of failures. Now we will understand what is the meaning of bearing capacity. Now we'll understand bearing capacity. Look at here, this is your foundation, this is your footing, and you are applying a load q here. Then this is your ground level, this is your hard strata, right? This is hard strata. Now this is your depth of footing and breadth of the footing. Look at here, whenever you apply some load here, this load is transferred to the ground and the ground will resist that load. No? This ground will resist that load. Understood? Okay, no doubt. Now let us consider this is 120 I apply and it is resisting 120. When I increase the load to 140, it will resist a 140. Then when I apply load at 150, then it will resist a load 150. When I apply 160, then it is not resisting 160, it is not resisting 150, means I can say that the soil is failed. Failed at what? Failed at 160. Any doubt? Means 120 is applied, it is resisted. 140 applied, resisted. 150 applied, resisted. But when I apply 160, then the soil got failed, means I can say that 160 is the bearing capacity of the soil. Any doubt? Right? This one, before that one, I will explain you what is the mean. Some terms are there. The first term is a gross pressure. Second one is the net gross pressure. Okay. Next one is a bearing capacity. Bearing capacity considered as a Q, and fourth one is a net bearing capacity. QN. Then fifth one I have ultimate bearing capacity, that is a QU, and sixth one net ultimate bearing capacity, that is QNU. Then I have another two, that is settlement pressure. Next I have seventh one, net safe bearing capacity, QNS, and eighth one is net safe bearing capacity, SBC, that is your QS. See here, you should observe this pattern: grass net, ultimate net. But when I come to the 7 and 8, first I write net and later I will write grass, SBC. No? You just remember this. Then after that I will write a ninth one. The ninth one is a settlement pressure, and 10th one is net settlement pressure. Okay. Next 11th one I have allowable bearing capacity, net allowable bearing capacity. 12 terms are there, we have to understand one by one. Right? Now the first one is a grass bearing capacity. Grass means just grass, how much you are applying. Therefore this is your applied load. It is applied means what is that applied? How much you are applying on this ground? Look at here, you are applying a q also, you are applying the dead load of this footing, you are applying the dead load of the footing, and you are applying this much of backfill. This is called as a backfill. This is a backfill, correct? Means how much you are applying? You are applying q divided by area, plus you are applying dead load divided by area, plus you are applying backfill. These all together is called as a gross pressure. Any doubts? Means it might be 120, it might be 140, it might be 150, I don't know. This all depending on your load, foundation and backfill, right? This is your gross pressure. Now if I deduct this gross pressure, out of that if I deduct backfill, then I will get a net pressure. Our net pressure is equal to, you can call just q divided by area plus dead load divided by area. This is your net pressure. Do you have any doubt here in these two terms? Digest these two terms, I will go forward. Gross pressure means coming from the superstructure plus dead load plus backfill. That is your gross pressure. Net pressure means minus backfill. No doubt, huh? Okay. Now very interesting. Many textbooks and many teachers and many students will misunderstand between the this one and this one. Okay, it is very important to understand gross pressure, net gross pressure and net pressure, and bearing capacity and net bearing capacity. Look at here. What is bearing capacity means? Bearing capacity, you have to say answer yes or no to answer this bearing capacity. If your foundation is resisting the gross pressure, then that is called as a bearing capacity. Then if your foundation is resisting the net pressure, then that is called as a net bearing capacity. Means the definition is somewhat same. This is also q divided by area delta l dl, that is your dead load divided by area, plus this is a backfill, this is your bearing capacity. Then this one what? Q divided by area plus dead load divided by area, but no backfill. This is your net bearing capacity. Means here what is this bearing capacity? Bearing capacity is this 120 or this 140 or this 150. These are your bearing capacity. Then what about this 120 and this 140 and this 150? This is your gross pressure. Then what is the difference between these two? I think you got an idea. Do you have any doubt here? Gross pressure and bearing capacity?
ಸರ್
Ah,
ಸರ್ ಏನು ಅಪ್ಲೈ ಮಾಡ್ತೇವೆ ಅದು ಗ್ರಾಸ್ ಪ್ರೆಷರ್ ಅಂಡ್ ಏನು ರೆಸಿಸ್ಟ್ ಮಾಡ್ತೇವೆ ಅದು ಬೇರಿಂಗ್ ಕೆಪಾಸಿಟಿ.
ಕರೆಕ್ಟ್. ಬೇರಿಂಗ್ ಕೆಪಾಸಿಟಿ ಅಂತಂದ್ರ ಸಾಯಿಲ್ ಹೇಳ್ಬೇಕದು. ಈಗ ಹೆಂಗಂತಂದ್ರ ನಾವು 120 ಅಪ್ಲೈ ಮಾಡ್ತೀನಿ, ಸಾಯಿಲ್ 120 ತಗೊಂತು ಅಂದ್ರ ಸಾಯಿಲ್ ಅಲ್ಲಿ ಬೇರಿಂಗ್ ಕೆಪಾಸಿಟಿ 120 ಐತಿ. ನೀನ್ ಅಪ್ಲೈ ಮಾಡಿದ್ದು 120, ನಿಂದು ಗ್ರಾಸ್ ಪ್ರೆಷರ್ 120 ಐತಿ, ಹೌದಾ? ಬಟ್ ನೋಡು ಈಗ ಪ್ರಾಬ್ಲಮ್ ಎಲ್ಲಾಗ್ತದೆ ಗೊತ್ತಾ? ಇದ್ರದ್ದು ನಿಜವಾದ ಅಂಡರ್ಸ್ಟ್ಯಾಂಡಿಂಗ್ ಯು ವಿಲ್ ಗೆಟ್ ಇಟ್ ವೆನ್ ಐ ಅಪ್ಲೈ 180. ವೆನ್ ಐ ಅಪ್ಲೈ 180, ದೆನ್ ಎಷ್ಟೈತಿ ಗ್ರಾಸ್ ಪ್ರೆಷರ್ ಅಂತಂದ್ರ ಯು ವಿಲ್ ಸೇ ದಟ್ ಗ್ರಾಸ್ ಪ್ರೆಷರ್ ಈಸ್ 180. Then how much is the bearing capacity? Bearing capacity is 160 only. You cannot say that bearing capacity is 180 because soil will fail at 160. Then 180 cannot be the bearing capacity for the soil. Now you got the difference between those two?
ಎಸ್ ಸರ್, ಎಸ್.
Okay, now 180 is a gross or net. Then below whatever the numbers, same numbers I have written here, but 120 I will not write because 120 is more than the capacity, right? Now look at here, I will come to the next one. What is the meaning of ultimate bearing capacity? Now we will switch to these two terms. Now I apply 120, it is safe, soil is safe. Apply 140, soil is safe. Apply 150, soil is safe. Apply 160, soil is safe. Sorry, soil fail. Correct? Then now look at it. When I apply 170, that is fail. 180, soil fails. 200, soil fails. Now, out of these, the very interesting point here is this is 160. How to define this 150? What is this 150? This is the, if you are looking at the top portions, then you will say this is the maximum load that can be applied on the soil without a failure. Correct? Without failure. Then that is your bearing, ultimate bearing capacity. Correct? That is the maximum load. Here I am writing that is the maximum load that can be applied on the soil without shear failure. That is your when soil fails in shear is called as ultimate bearing capacity. Now look at here. You go by bottom. If you go by bottom, what happens? 160 is lesser than 200, lesser than 180, lesser than 170. Therefore, what I can say, 150 is a minimum pressure. Minimum pressure the soil can take safely is also ultimate bearing capacity. Both are same. If you are saying maximum, then you are coming from the top. Then if you are saying minimum, then you are coming from the bottom. Understood? This is your ultimate bearing capacity. Then what is the net ultimate bearing capacity? Minus backfill. That's it. Okay. Ultimate bearing capacity QU you got. Then what about QNU? QNU is QU minus backfill. That's it. Now coming to net safe bearing capacity and safe bearing capacity. Now look at here. I will ask you one question. This is your building. This is your building. Building is ready to apply 160 that load. Then whether your soil is ready to take that load, consider the same example. Whether your soil is ready to take that load, yes. Why? Because your ultimate bearing capacity is also 160. Ultimate bearing capacity is 160 and you are applying grass pressure is also 160. Therefore, this entire thing is safe. Okay, will you consider 160 and design your foundation, or will you underestimate the capacity and design? What do you do? While designing, will you consider 160 and design, or you will underestimate? Hmm?
Considering, sir.
You will not underestimate. Now look at here. There is one person. This person will die when I apply 160 kg. Now, will you apply 160 kg? Will you apply 160, or will you design this person with 160 or lesser than that?
Lesser than that, sir.
Lesser than that, no? Because now look at here, you will tell that how many people will be there. ನೀವು ಕೇಳ್ತೀರಿ ಅವ್ರು ಮನಿ ಕಟ್ಕೊಡ್ರಿ ಅಂತ ಹೇಳ್ತಾರೆ ಅವರು. ಅವಾಗ ನೀವು ಹೇಳ್ತೀರಿ ಯಾರ್ಯಾರು ಇರ್ತೀರಪ್ಪ ಮನಿ ಒಳಗ ಅಂತ ಕೇಳ್ತೀರಿ. ನಾವು ಒಂದು ಇಬ್ರು ಗಂಡ ಹೆಂಡತಿ ಇಬ್ರು ಮಕ್ಕಳು ಇದೀವ್ರಿ ಅಂತ ಹೇಳ್ತಾರೆ ಅವ್ರು. ಅಂದ್ರೆ ನೀ ಏನ್ ಮಾಡ್ತೀವಿ 4 ಮಂದಿ ಅಂತ ತಿಳ್ಕೊಂತಿ. 4 ಮಂದಿಗೆ ಎಲ್ಲ ಡಿಸೈನ್ ಮಾಡ್ತೀವಿ. ಆಮೇಲೆ ಜಾತ್ರೆ ಇರ್ತದ, ಮನಿ ಒಳಗೆ ಮದುವೆ ಇರ್ತದೆ, ಎಲ್ಲರೂ ಬಂದ್ಬಿಡ್ತಾರಲ್ಲ ಅಲ್ಲಿಗೆ. Then you should design it for more loads. Means you have to underestimate the capacity. Therefore, you will make divided by factor of safety. When you make divided by factor of safety, then you will come to the definition called as a safe. That's why here what I have to understand is net CF bearing capacity is net ultimate bearing capacity divided by factor of safety. Then safe bearing capacity is ultimate bearing capacity divided by factor of safety. Okay na? Now what is your safe bearing capacity? Safe bearing capacity equal to net safe bearing capacity plus gamma d. Then net safe bearing capacity is nothing but what? Ultimate bearing capacity, net ultimate divided by factor of safety and gamma d. Then what is this net ultimate bearing capacity? That is QU minus gamma d bracket divided by F plus gamma d. This is your safe bearing capacity. Any doubt? Okay, now you got a safe bearing capacity. Now look at here. If I want to say the foundation is safe, what I have to, how many criteria I have to satisfy? Huh?
Shear strength and settlement.
Very good. Two criteria I have to satisfy. One is the shear criteria, and the second one is the settlement criteria. The first one is the shear criteria. What it says is the soil should not fail in shear, means that will be taken care by safe bearing capacity. Means your QS will take care of the soil is not failing in a shear criteria. Now coming to here, the settlement criteria, when I see the settlement criteria, then net settlement pressure athwa that settlement pressure Q rho I will call. Q rho will take care of the settlement criteria. Means if your load is less than this one, then you are within the permissible. If your load is less than this one, then you are safe in shear criteria. Now let us consider 160 is your safe bearing capacity and 150 is your net settlement pressure. Then how much you will consider and design a footing? You will consider 160 and design or 150 and design? You will consider 160 and design or 150 and design? Huh? Net settlement pressure is 160, bearing capacity is settlement pressure is 150, bearing capacity 160. How much you consider for design? No idea?
160.
150.
160,
150.
150. Least of these two you have to consider. Right answer. You have to consider the least of these two. Why? Because it has to be safe in both the side. That's why you will consider 150. Then this 150 is considered as allowable bearing capacity. This is your allowable bearing capacity. Right? Now, allowable bearing capacity means what? ABC is a least of SBC and settlement pressure. Settlement pressure over. Right? Then net allowable bearing capacity equal to allowable bearing capacity minus gamma D. That is your backfill. Do you have any doubts in these 12 terms? No doubts now? Then we'll go ahead. Now, almost this chapter is over because you don't no need to remember the derivation. Therefore, we have to by heart the formula and we have to go ahead. Now, look at here. Usually, we will be concentrating on safe bearing capacity. Safe bearing capacity is equal to the load applied divided by area you can consider, or this is one formula, applied load divided by area, and another formula you can consider it like qns divided by f plus gamma d. This is further qns means, the further qns means what? uh, qnu minus gamma d divided by f ಅಲ್ಲ ಬರ್ದಿದ್ವಲ್ಲ ಎಲ್ಲಿತ್ತು qns plus gamma d qnu plus f. Okay, 1 minute. Safe bearing capacity equal to net safe bearing capacity plus gamma d. Correct? Now what is the net safe bearing capacity? Net safe bearing capacity is nothing but net ultimate bearing capacity divided by factor of safety plus gamma d. Then what is the net ultimate bearing capacity? that is ultimate bearing capacity minus gamma d divided by factor of safety, then this as it is gamma d. This is your QS. Out of these, F you can assume are given, gamma you can assume are given, depth will be given. Means out of these are all very important, those parameters will be given. Then we have to worry about is ultimate bearing capacity. Then ultimate bearing capacity derivation will be there, that is not required here. Then after derivation, we will be having the equation. Then before derivation, we will be making some assumptions. Those assumptions we have to remember. The assumptions made by this derivation is done by Terjagi. This is done by Terjagi. Then the assumptions also by Terjagi. The first assumption is general shear failure. The second assumption is strip footing. Second assumption is strip footing. The third assumption is passive earth pressure concept. Passive earth pressure concept. Fourth assumption is that first zone, that is wedge, triangular wedge, is considered as part of the footing. Part of the footing. So, no? And very important assumption is water table is ignored. Water table is ignored. These assumptions are considered and he derive an equation. That equation is QU equal to CNC plus gamma D NQ plus 0.5 gamma B N gamma over. This equation you have to remember. Right? Now, it is very important that from now whatever I explained there is very important how to remember this formula, and there are many factors will consider, because see here the assumption says that general shear failure he considered and derive the equation. What if it is a local shear failure? He considered strip footing and derived the equation. What about a circular footing, rectangular, square footing and rectangular footing? No, he considered a passive. Okay, don't worry. He considered this one. Don't worry. Okay, whatever. What happens if water table appears in future? Then what corrections he has to apply? No, these points we have to discuss and we have to implement in the bearing capacity equations. Therefore, here this equation further it becomes what? CNC SQ DQ IQ plus gamma DNQ, sorry, NC. Okay, CNC SC IC gamma DNQ SQ DQ IQ plus 0.5 gamma B N gamma S gamma D gamma I gamma. Now this equation is Indian standard equation. Indian standard equation. Understood? Huh? Of course, many factors are given by Terjgi only. This shape factor, S means shape factor, D means depth factor, I means inclination factor. These all factors are given by Terjgi only, but still IS code has written in the equation itself and few modifications are done. Don't worry about these all these factors. Just I will give you one table. That table you by heart it. No? Now in your page you should write a equation in this way, that is a QU equal to CNC plus gamma D NQ plus 0.5 gamma B N gamma. You write it like this big, no? Widely you write it. Then you make one column here, one line here and one line here and one line here. At this line you write a property, and here you are writing the factors which are factors which we need to multiply to this term, and here we will write a factors need to multiply to this one, and here we will write a factors need to multiply to this one, right? Now if factor is 1 1 1 means the equation will not be altered. Then if it is a local shear failure, then here you have to multiply 2 by 3, then 1 1. Understood? Means what is your equation for local shear failure? 2/3 of CNC plus gamma D NQ plus 0.5 gamma B M gamma. Now if it is a strip footing, then 1 1 1. No factors need to multiply to that equation. Then if it is a circular footing, then here you have to multiply 1.3 or 1.2 also you can remember. 1.3 will remember. You know? 1.3 and here 1 and here you have to multiply 0.6. Okay, textbook you will be seeing here they will multiply here 0.3, but concentrate here. In our equation we have already written 0.5 and here I am writing 0.6. Therefore in textbook you will be seeing 0.3. Okay, don't worry, both are same. Here I am writing 0.6. Then if you are having a square footing, then here you multiply 1.2, 1 and 0.8. Right? Square. I always remember it like this. I will use a one hint to remember this one. The hint is this 6. I will write it like this because this is circular. In the 6 there is a circle, but this 8 instead of writing like this we will write it like this, 0.8. Right? This is a 0.8 because it is circular square. In some textbook they will write it here also 1.2. Don't worry, that is also 1.2 and 0.6. Don't. Next, if you have a rectangular footing, now look at here, this 1.2 is altered like this, 0.2 b by l. This is 1. Then here we will be multiplying 1 minus 0.2 b by l. Right? Any doubt? Now, if you have a continue, if you have a sandy soil, then what happens? Sandy soil means c equal to 0. This will be 0, then 1, 1. Then if it is a clay soil, then NC equal to 5.14 for IS and NC equal to 5.7 by terjgi and 1 and 0 here, 0 both. Okay, now this is clay. Now if we have a water table here, then you will not multiply anything, and here you will multiply RW1 and RW2. Okay, the meaning of RW1 is that equation will be there, don't worry. That is your 0.5 into 1 minus ZW1 by D, and this one is RW2 is equal to 0.5 into 1 minus ZW2 divided by B. Right? Over. If you have any doubts you can ask. Do you have any doubts? One more, we will continue this table. See here, water table at ground level 1.5, water table at footing bottom, then 1.5, then water table greater depth 1 1 1. Any doubt? Okay, this much is all about bearing capacity. Okay, we will quickly go to pile foundation. This one, the plate load test. Plate load test is very familiar concept for students because this you will study in third semester also, and after that when you come to foundation also. You know, you will be knowing this one. B students, most of the B students will be knowing this one. And if you want to see the pile found this plate load test, you can go through Google and just watch some of the images which are conducted practically. Here we will be having plate load test means what? Plate will be there, no? We will be having plate. Then we should remember the first thing about the plate. The plate can be a square or circular. Square or circular. Whatever that, it might be square or circular, you will be having in three dimensions: 30 centimeter plate, 45 centimeter plate, 60 centimeter plate, nowadays 75 centimeter plate. Okay, and thickness of the plate will be 2.5 centimeter. Any doubt? One very important point is there, and even no, 75 centimeters already is there. Now this 45 centimeters is there, no? This will be used. This will be used when for clayey or silty soils, clayey, silty or loose soils. This 45 centimeter plate will be used. In case of dense soil, this will be used. In case of dense sand or gravel, in case of dense sand and gravel, you will use a 750 mm. Right? Okay. Sometimes what happens, whenever you use a 750 mm plate, then when you put a load here, then there is a chances of bulging this plate, bending this plate. Therefore, a 750 mm, then above that you will put a 60 mm, then above that you will put a 45, then above that you will put a 30 centimeter, then you will put a load so that this will not bend. Okay, this practice they will have in the plate. This is all about plate. Any doubts in the plates? No doubt. 30 centimeter, 45, 60, 75 plates. Four types of plates are there. 75 bigger plate is for dense sand and gravel, and smaller plates are for clay, silt and loose. Right now. Now coming to the pit. Coming to pit. You know that these plates are kept in the pit. If you are keeping that plate here, then this is considered as a BP. BP is the breadth of the plate. Then this width of the pit must be 5 times the BP. Then the depth must be your depth till hard starter. Okay, this is all about a pit. Right? Now loading arrangement. Loading arrangement. To resist the load, you will be using a truss. You will be using a determinate truss, or you will be putting the sandbags. You will be putting the sandbags. Now these sandbags are put on the platform. Then you will put your this one hydraulic jack. Then you will put a proving ring. then it will push down and proving ring will read the readings. Right now, some very important points we have to note it down. The important points are the seating arrangements we have to give. That is seating load. Seating load we have to apply 0.7 or 0.7 ton per meter square or 70 gram per centimeter square or 7 ton per meter square. You have to apply seating load. 7 kilonewton per meter square. This is your seating load you have to apply. After seating load, you have to increase the load. After seating load, after seating, you have to increase load at a rate of one uh, at a rate of 10 ton per meter square. 10 ton per meter square or one fifth of estimated bearing capacity, whichever is less. Correct? This is all about load increment. Then the settlement. Now you have to study the settlement. Then the settlement you are studying it at an interval of one 1 minute, 2 minute, 4, 8, 16, 30, 40, 30 or 1 hour, 2 hour, 4 hour, 8 hour, like that you have to increase. Till what? Till the settlement become constant. Now look at here, very interesting here it is settlement. First you will apply 10 ton per meter square, correct? See, consolidation chapter you remember. Here you are applying 10 ton per meter square load. When you apply 10 ton per meter square, then you are recording the settlement. Then when settlement stops here, then you will apply 20 ton per meter square. Then you will read the readings. Then you will increase 30 ton per meter square. Unlike settlement, this consolidation, don't double it. 30 ton per meter square. Then 40 ton per meter square. Like that, you will increase the load. Right? Now, after this, you will draw the graph. The graph which is already shown, already explained. You will get a general shear failure, this nature, and local shear failure and punching shear failure. Okay, this is already explained. Now, calculation of settlement. Calculation of settlement. Calculation of settlement, for that look at here. Okay. Now this is your Q value, that is the load or pressure. Then this is your settlement. Now this graph is drawn for plate. This graph is drawn for plate. Therefore I will write it, this is a QP. This one I will write it as a SP. Now if you want to calculate it for the foundation, then for the foundation I will write one, give you one chart. Settlement calculation and load calculation. In this one I will make another two, that is sandy soil and clay soil. Sandy soil and clay soil. Okay, now sandy soil settlement calculation. First, which is smooth? Sand is smooth or clay is smooth? Which is very smooth? Clay is very smooth. Therefore, equations are also very smooth. Okay. Load equations for clay QP is approximately equal to QF. Okay. Here QP divided by QF equal to BP divided by BF. Right? Now when you come here, this is your SP divided by SF equal to BP divided by BF. This is also load calculation only, no? 1 minute. This is correct. QP, that is correct, and here QP divided by QF equal to BP divided by BF. Correct? Now coming to settlement. Settlement for clay. Settlement for clay is SP divided by SF equal to BP divided by BF. But here settlement for sand, SP divided by SF equal to BP divided by BF into point BF divided by BP minus zero point 0.3 minus 0.3, an entire square. Right? These equations you have to remember. This is all about plate load testing. Okay, now coming to standard penetration test. Standard penetration test. This is called as SPT. This SPT we will go to the ground. This is the ground, and we'll put a tripod here. The one tripod, the another column, then another one. Okay, now at this tripod we will arrange some arrangement here. Then we will have one rope here. Okay, then this will be tied with the one load here. This is 65 kg. Okay, then after that we will be having some arrangement here, then this arrangement, and after that we will be having one sampler. This is called as split spoon sampler. Okay, then this hammer is pulled here and it is dropped from the height of 75 centimeter. When you drop, this will hit inside, it will go inside, then it will go first 150 mm. This is ignored, that is seating. Then the next 150 and next 150, total 300. Here count n values, count blows. You know how many number of blows you are going to give, that you are going to count. This is considered as SPT n value. Over. Do you have any doubts?